Hello, welcome back. In this segment, I want to talk about how to choose a uniform group element. In cryptography, we deal with finite groups, and oftentimes we want to randomly select an element. Okay, randomly or uniformly, they are both interchangeably the same. So, how do we go about choosing a uniform group element in polynomial time? Okay, so more formally, we need a group. Okay, the group could be Z star N or Z star P. Those are the groups that we talked about earlier. And we need to know the bit length L. Okay, how many bits do we need to represent each element of the group? Okay, if the number of elements, for example, if we take Z star N, okay, each element is there an integer, so you can easily compute how many bits do you need to represent one particular element, and you take the maximum of that becomes the L. Okay, which means you can put a padding of 0 in the beginning so that all the group elements will be represented using an L bit representation. Okay, so L denotes basically the element length. Okay, if element requires less than L bits, then you can put a 0 in the front to make it L bit. Okay, and then we also need a third parameter, the number of attempts we will allow the algorithm to try before terminating. Okay, all right, so those are the three inputs, and we will get an output, a uniform group element. Okay, so the algorithm is as simple as this. We will try t times from 1 to t. This is a very high level algorithm, not necessarily easy to program directly, but I will show you a particular instantiation of this algorithm later. Okay, so we'll try t times. In each attempt, what are we trying to do? We choose uniformly choose a random element x from the set of length L bit strings. Okay, this basically means you have L bit binary strings and you are choosing one of the string. Okay, and we check whether that particular element that you have chosen is in the group G. If it is, then you return X. Otherwise, we try until we exhausted all the T atoms. Okay, if we are not able to succeed, at the end we return fail. Okay, that's all. So this is basically the idea. Since X is chosen uniformly or randomly from this set of all possible strings of length L, X itself is uniform. Therefore, if X is present in the group, we can say it is a random group element because the input X itself is a random uniform element. Therefore, and if we confirm that element is also present in the group, then we can say X is a uniform group element. Okay. Now the question is, how good is the performance of this algorithm? What is the probability that we will fail? Okay. Of course, we would like the failure probability to be as low as possible, right, or as small as possible. How do we make sure that the failure probability is very, very small? Okay, so let's think about this first. How do we compute failure probability? So we fail only if we are not able to find an X in all the T atoms, right? Okay, so what is the probability of success then? Probability of success is simple. We need to get to this particular branch of the code. So how do we find out when will we get the return X? Okay, how many elements are there in our universe of all possible L bit strings? Okay, we have 2 power L elements, right? If L is the bit length, then the 2 power L is the length of the possible strings. Okay, if L is 4, then there are 16 possible strings, zeros and ones. Okay, 0, 0, 0, 0, 0, 0, 1, and so on. You can write it. There will be 2 power L strings. Okay, how many elements are in the group? Okay, let's assume the number of elements in the group is denoted by the cardinality of the group. Okay, divided by 2 power L. So probability that we successfully return a random element in the group is G over 2 power L. Okay, the number of elements in the group divided by 2 power L is the probability. Okay, obviously number of elements cannot be more than 2 power L, so probability is always a number between 0 and 1 inclusive. Okay, so this is the success probability. This is success. Okay, so now come up with failure. Failure is nothing but opposite of success. So we should be able to say 1 minus this, right? That's the failure in one attempt, and we want to fail in all the T attempts. Okay, that means we can write it as, So the failure probability is now as simple as 1 minus, so when do we return failure? So we return failure if we don't succeed. That means 1 minus no success. That's the no success probability. Okay, this is 1 minus 2 power L is the no success probability. And we want it to fail all the time, okay, all the t times in order to hit the fail branch. So basically this is the failure probability. So it's 1 minus number of elements in the group divided by 2 power L power t. Okay, this is the failure probability. And now I will start building some expressions out of this and come up with an algebraic model for us to figure out what is the probability that we will hit the fail branch. Okay, I'm going to use, excuse me, so I'm going to use a constant k as, let's assume I define a constant k as follows. Let's say the constant k is nothing but 2 power L by the number of group elements. Okay, all right. So that means we can rewrite this as 1 minus 1 by k, because we just inverted, right? Power t. Okay, power t. Now I'm going to make some assumptions about the t itself. This is power t. What if t is, let's assume t is just k times some security parameter n. Okay, I'll explain what small n is in a moment. Let's say t is k times n. So what will we have? We will have 1 minus 1 over k, right? Power k times n. Okay, I'm assuming t is k times n. Okay, that's what I'm assuming. What is k, what is n? N is some kind of a security parameter. Okay, you could say what I'll explain first. N is some integer. Take it like this for now. Okay, so what is the value of 1 minus 1 by k power k times n? Okay, so now we can rewrite this as 1 minus 1 by k power n because of exponent rules. That's the exponent, first exponent, and then you put another exponent n. Okay, but we have a nice model now. We do know the behavior of 1 minus 1 by k power k. Okay, 1 minus 1 by k power k is less than or equal to the value e, which we use in mathematics, the natural log base e. Okay, so there's a nice expression that tells us that 1 minus 1 by k power k is bounded by e reciprocal of e, which means e inverse. Okay, so e inverse power n means e power minus n. Okay, so we have a nice model now that the probability of failure is bounded by e power minus n. Okay, so now I'll explain what the small n is actually. Okay, suppose you decided to have a very small failure probability. Okay, which means you could say choose n to be 40. Okay, that means the probability that you will not be able to select a uniform group element will be bounded by e power minus 40, which is a very tiny number. Suppose you say, well, I want more confidence, then you could say my n will be 80, and then the probability of failure is really small, 1 over e power 80, which is pretty much close to 0. Okay, so you could choose depending on your requirements, what is the failure probability you would like to tolerate. Remember, our goal is to succeed oftentimes, to find an element present in the group, but we still wanted to figure out how often this algorithm will fail. For that, we need to have some parameter n to reason about. Okay, having the notion of n defined informally, we can now think about the properties of the k that I talked about earlier. Okay, what is k? Well, t, that's the input, user input t, which is the number of attempts to run this for loop. We defined t to be k times n. Okay, that's how we assumed that. You see here, t becomes k times n. Okay, n is the security parameter. Okay, small n is the security parameter. You define n such a way that this probability is so small. Okay, and now the question is, what can you say about k? So as long as k is just a polynomial in n, your t will be polynomial in n, right? Because k is a polynomial n multiplying with n is still a polynomial. So if you want a polynomial time algorithm, right, for your for loop, this t must be a polynomial, right? Otherwise, this is not a polynomial time algorithm. So in order for this for loop to run in polynomial time, the only expectation is that the value k is a polynomial in n. Okay. What is k? K is nothing but 2 power L. L is the length of each element, okay, each group element. And we divide that by the number of elements in the group. Okay, this is the k. Okay, if this value k is bounded by a polynomial in n, then we have a polynomial time algorithm. Okay, that's basically it. So we know how to choose a uniform group element in polynomial time. All right. In the next segment, I will show you how to choose a uniform group element from a particular group. I will instantiate Z star n, one of the important groups in cryptography, and show to you that you can easily choose a uniform group element in polynomial time. Okay, just to summarize the long story short, all we need to do is make sure that the number of atoms that we are trying to execute, t, right? T is the number of atoms. That means the for loop will run t times. If we can make sure that t is k times n, where k is nothing but 2 power L by the number of elements in the group. Okay. If t is k times n and k is a polynomial in n, then this overall algorithm will run in polynomial time. Okay. N is a security parameter. You could choose n to be a large value such that the failure probability is bounded by a very, very small number, meaning the algorithm will always succeed in finding a uniform group element with very, very high probability. Okay. So as a user of this algorithm, you have to choose t. And in order to choose t, you need to know k and n. K is easy to compute if you know the number of elements in the group, and 2 power L divided by the group will give you the k, and n is the security parameter that you choose based on what is the probability of failure you would like to allow. Okay, that's basically it. Thank you very much.